Okay. So this is will be our last seminar series. So information geometry is a big area, but I only covered projection, information projection only, which is actually quite important in statistics. So this is a particular example that I'm going to address. So suppose you have a moment information. Okay. So then you can think of all possible, right? All possible distribution with the moment condition. So then this is kind of M flat, right? And so then we use generator convex function to develop a Bregman divergence. So is something like this, and then we can basically develop projection. So we can call this Bregman projection, Bregman projection, which is more generalization of the information projection, right? And this is a quite nice because this is a basically convex set, uh, and closed and convex set, and then this is a divergence measure, and so this is outside. So you have a space Q and outside P0, right? And so the deviation here is essentially Bregman divergence. So I so so then a question is we want to characterize this point, right? We want to Q star. So we want to characterize this particular point, projection point. So so what I mean by characterize? Well, actually, this guy, because you, okay, here the point is this guy Q is actually QM, right? Given M, right. So this is actually you can write it as a QM, right? Because it depends on M. And so as you move M along, right? As you move your M, then your space changes. That means your projection will change. So then that means actually this projection is also a function of M, right? And then but this pass, so it's like you have several different Q spaces, right? Layers, and then this basically create a pass Q star, right? So that is so you have a M flat. So if we know that if this Bregman divergence is a Kullback-Leibel divergence, then this pass is actually E flat, right? E flat uh, pass, basically exponential family, right? But now we want to generalize it with a more general divergence. Then the space this pass is not really E flat pass, but it's a different pass. So we want to characterize. So this is another flat space. So that is a dually flat because Q itself is a flat, but and then it's a dually flat. So then how we can actually so then the projection indeed induces a model, and so how you characterize the model, something like that. And then furthermore, if your M is a functionable, so now your model is this. Okay. So suppose you have this one model, then how do you construct this M projection? I mean the Bregman projection and develop information theory. Okay. So that is the specific example that we want to address so that we can have a better understanding of this projection. So here, so the space we are interested in is a property space. And then there's a inner product. So it is called pairing. So this is one parameterization. And so this pairing is eventually has to do with the duality, but we'll see soon. And then G is a convex set, right? So a strict convex set we want to use to create a divergence, and then this is F is uh, Legendre transformation, convex conjugate function. And then the constraint that we are particularly interested in is this kind of a constraint. So that is a moment condition, right? We have a moment condition, and then this is a kind of semi-parametric model, right? And so then basically we want to apply projection break using the Bregman divergence measure for this under this semi-parametric model. Okay, so that is the standing assumption and notation. And I will briefly review some basic concept that we covered in victory lecture again. So this is a convex conjugate function, right? So this is a dual function that we will use. So one of the important property is the Fanchel-Young inequality, which is this one. So notice that we have two different parameterization, right? So this is a dual parameterization. So one is eta, the other one is p, and then this is a pairing, and then turns out that for any, so this is for any. Okay, so this, basically we have a two coordinate system, right? I should have moved this. It's not important. So we have a two coordinate system. One is the using p, the other one is using eta, right? So then, and then from p we have a convex function g, and from eta we have a convex function f, convex conjugate function. And then for any point p and eta, we have this inequality, first of all. But if this guy and this guy are connected through this, okay, then we have equality, okay, right? So so basically we have a mapping. So given p, we apply nebular, inverse delta of, what is the usual notation we call, what, do you know, anyone know how to call this?
It's all about nebula.
Huh?
No. Yeah, no.
Nebula? Okay. Okay. So okay. So basically, right, given P, we apply nebula G to obtain to construct identify point eta, right? And then the other one is same thing with the convex conjugate function. And then that means they are actually we have a one-to-one mapping. Okay. And so that is first inequality. We covered this already last class. So basically, in that sense, we can kind of create a mutual invertibility. So we have a two space. So omega is this space, and omega star is this space, right? Something like that. And so then this nebula G is from omega to omega star, while nebula F is omega star to omega. And so then we have a mutual inverse and diffeomorphism. So I think that it means just the one-to-one, essentially. So, so, so inverse function of the nebula G is nebula F, and same inverse function of nebula F is nebula G, right? Okay. Yeah. Okay. Maybe I will just read the proof. So from function Young inequality. So if we have equality at the unique maximizer, right? And so then the envelope theorem basically says that we don't have to worry about the Lagrange multiplier. So if you just take a differentiate with respect to lambda, I mean with respect to eta, then basically you have a see I think the point is okay if you differentiate eta, then you have a p minus nebula g p, right? So you have a and so then because p, you can write right. So what does that mean? I think
And evaluate that P where nebula GP, then second term goes zero and first term.
right. Okay. Thank you. Right. So this guy, because of the envelope theorem, we can basically ignore when it comes to eta, right? Differentiate with respect to eta. Is that your point? No?
Maybe some more terms are inside there, but at the end only P remains.
Yeah, right. So that is the envelope
is the
theorem,
envelope theorem.
right. Because envelope theorem basically view the you don't have to worry about round round at round p, something like that. You don't have to worry about that. That is the
Yeah, that's the
basically
visual, yeah.
right. That's so that means you just ignore.
But P minus nebula GP
Oh,
and only
okay.
remain P is actually wrong.
Okay, right.
But the result is only remain P is right. Yeah.
I see. The first one,
Yeah, only P remains.
right? Only p remain,
Yeah.
but right. So because okay, let me explain. I guess. Okay. So yeah, that is confusing, but I think so. This is so you differentiate with respect to eta, right? So okay. So you differentiate with respect to eta, then that will give you a form of the solution, and so then you wonder. So this is a p plus p times basically p no eta, right? P eta. But point is that this one you don't have to worry about This guy.
Oh, no. The first derivation is given eta,
Okay.
and we want to find the conjugate of eta p as a function of p eta. This is the first step to define the Legendre dual.
Right.
And once we find p eta as a function of eta, and then again we take a derivative with respect to p, then two step.
Right. So basically here, just nothing, right? I mean, just I think
Just solving the Schur-Freeman problem. This is
right.
Yeah.
So I mean this one, right? Okay. Well, somehow I kind of
the first step is finding p that makes that function Schur-Freeman. This part. The first part is just solving this one.
okay.
And after we pick this p,
Okay.
that will be input of this, and then again we derivate of respect to eta.
Right. So somehow I think this is not difficult problem, but somehow
we already
I'm right.
victory, but
Yeah, right.
confusing.
So yeah, right. The maximum. So P star, right? Okay. This P star supposed to be so the P star the maximizer, right?
Yeah.
Is
P eta.
P P eta, right?
Yeah.
P eta, which is okay, solving eta minus nebula P, nebula GP. Is that
Yeah, that's
right?
Yeah.
And so that is actually I see G, you mean something like this,
Yeah.
right?
Yeah.
And then this is actually F. Okay. Right? But this is not necessary, not needed. Yeah, so yeah. So this is right. I think this is okay. I think this is needed. Okay, this guy is F, nebula F, by the definition of the convex conjugate, right? So that is how we obtain this as a solution. Yeah, one of the important property of convex conjugate function is this property. I mean yeah, this is what we actually want to show, right? This is actually what we want to show. We want to show that G delta inverse is I mean nebula G inverse is nebula F. Okay, so that's the dual, one of the important property of the duality. Okay, well, let's just move on. And then furthermore, okay, so furthermore, so this is basically right. Basically, this result basically says G inverse nebula G nebula F inverse is nebula G. Vice versa, right? Okay. The only thing is that F has a domain eta level, while G has a domain in P level. That is the difference. And then same way, Hessian, we can actually use this inequality, equality, and differentiate again further. Then we can get this inverse Hessian formula. Okay. Now, so this is actually we covered already last class, and now let's move on to this is important thing. So now we're gonna use G as convex function G and construct the Bregman divergence, right? And so this is the definition, the Bregman divergence definition. And now we use the facial Young equality at this point, right? So if you use this equality at this point, because we know that when the equality at the Fancial Young inequality holds, then we can basically express. So basically, this guy is eta q. So we subscript. Okay. So remember, we have a two space, right? And so this is a PQ. Suppose we have PQ, then the transformation, right? Applying the nebula G. So if you apply this transformation nebula G, you have a point that is called eta P, right? So basically, eta P is nothing but nebula G over P. Same way, you can use Q, apply the same function, which is actually eta Q nebula G Q. Okay. So that means you can now write this guy. So this guy is same as this one, and then you write this one, and so then basically you can do algebra and show that, check that so this guy is GP minus GQ minus eta QP plus eta QQ, right? And then you can simplify further, because you have this guy and this guy to so what is this? This is actually sum of the two is called F. So what is F? Remember, what is FQ? FQ is GQ plus eta QQ. No, is it minus, right? Minus and plus eta QQ, right? And so you use that. So basically, you so you have equality. We have equality because of that. Okay. So that gives this equality. And then basically now you express this GP, same thing, right? GP is GP is FP F eta P. Okay. So use this, right? If you use this, then you can also do some further simplification. So you get this one, which is Bregman divergence. So this is a really nice result, because you see, end of the day, so you don't have to worry about all this derivation. You just, the only thing we need to know is this one. So what that means what? So there's actually equivalent, right, expression. So the left side is a Bregman divergence in this space, right? In this space, PQ space. And this is the Bregman divergence in the right space, right? Because they are dual, one-to-one. So whatever the distance between the 2 points should have something corresponding concept in the other side, right? It's like you can think of a meter, right? Meter. then just your left hand becomes a right hand if you look at meter, but it's actually same, right? So that's exactly doing here. So the only thing is that your dg in prime variables equals the Bregman divergence in so df in dual variables. So the only difference is that the order is kind of the opposite, but other than that, it's same. So in that sense, previously in lecture one, I kind of distinguish between E projection and M projection, right? But at the end of the day, they are dual, so it really doesn't really matter. Okay, just the information projection. I mean Bregman projection. Okay, now so let's move on to constraint geometry. Okay, so remember we want to apply constraint optimization, and the optimization is a Bregman divergence, right? And then constraint is kind of this linear constraint. Uh, so this is a particularly interesting, subspace. But if you view it as a mapping, okay, so if you view it as a mapping, I mean this one, so linear functional as a mapping, and then the derivative uh, has a so the Frechet derivative of the linear functionals are represented by one and y. So if you naively think of differentiation with respect to p, right, then what you're left with is one and y. So that is indeed a basis for the other dual coordinate system. So see here, remember we have dual. Here we have basically uh, one and constraint is one and m. So it's a q, right? So q is characterized by one and m, but the corresponding dual direction, so dual direction. So this is one and m is basically a kind of constraint assigned to p, characterizing p. And now you have you basically in this coordinate system, you basically have one and y. Okay. So we are not really projecting yet, but it characterize a dual plane. So you have a space spanned by one and y, okay, but you have a kind of a reference point. So see from here, remember from here, this is the omega, right? Omega space. This is omega prime. And so from here to from omega to omega prime, we have a nebula G, right? So then the reference distribution, okay. So see, we eventually we want to do some sort of projection, right? Projection. So then if you want to do that, then the projection, the reference point can be outside. This, if you, I mean, if this is a subspace, yeah, okay. Maybe I will. So this is your omega, and Q is just a small plane. I mean, small plane, and then this Q is characterized by this constraint, right? In three, and now you have a reference point outside because you want to do projection later, right? And then basically we and then so then if you yeah, so any point so we want to do something similar to here, but then here you have a dually flat space which is a span by one and y, right? but there's a lot of different subspace. So you need to have some uh, okay. So you want to have this guy. So you need to some relevance to this initial point P0, right? So then we need to basically do some sort of transformation to here. So that is basically nebular G over P0, right? So that is this one. So that is this guy. Okay, you have some sort of a reference point, and then need a span. That is like if you think of exponential family. So what is the exponential family? You have something like tx or tx times zeta, right? Or sx, whatever. But you also have initial hx, right? I mean, so remember the exponential family has this form. So this guy hx or p0x is the initial point that you use for so this is actually solution to minimizing the KL divergence of p0, right? So the subspace is the space generalized by surface statistic, moment conditions on the surface statistics, right? And then this is the solution p star. So my point is that this p0 should be here, right? So that means this is actually if you think of a log, so this is actually log scale. So this is actually P0 plus lambda times or zeta prime S zeta, right? I mean, not S SX. So SX. So that is exactly same as what we are doing here, right? So this span corresponds to here, right? And then this guy corresponds to this guy because nebula G is actually log. So G is what is G? GP is a P log P, right? And so then nebula G is log P. Okay. So now you may understand what I'm trying to do. So basically, in lecture one, I introduced M flat and E flat, right? And M flat was actually invariant in some sense, in the sense that this is the same thing, right? The same M flat. So this is the same M flat subspace, but the E flat changes because we use different G. Okay, so if we use this particular G, right, then basically we have a E flat uh, derived from nebula G. Okay, but if you have a different G, different capital G, then you have a different form. So then generally we'll have something like this. So basically this is the of dual affine plane. Okay, and where this parameterization is remember this parameterization is nothing but uh, the transformation derived from nebula G, right? So you have a parameterization P here, you have a P origin point here, but you need to do uh, you, you apply this nebula G, capital G, to obtain a dual system, coordinate system, which is eta. Okay. So then this is basically a dual affine plane. Uh, So this is a subspace parallel to span one y, and that passes through the reference dispersion. Okay. So then you have a basically a parametric model essentially, right? You have a parametric model, and 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 then this parameter actually gives back your moment conditions. Like remember in the exponential family, uh, the a, right? A zeta gives the exponential t, something like that, right? And so that's the same thing here. Uh, Okay. By the way, what is f? Okay. So what is f q beta? So f q beta is uh, so you have this coordinate system, right? And then apply to the convex conjugate function f. So that this capital F has nothing to do with the CDF, it, right? It's more is is actually you know free energy or potential function. Remember in the exponential family, so so this guy is so remember. Okay, let me see. Uh, if you in the exponential family, something like that, we have a something like Sx minus a zeta, right? And something. So what is this a zeta is doing? A zeta is a dual. Is this guy actually? I think because for G, when GP is a is P log P, right? And then what is F for this one? What is F? Exponential function, right? Eta is exponential function, right? Because the differentiation of this guy is log G, log P. And so this guy is inverse. Inverse of log is exponential, right? So basically this is so basically this A is exponential of no. We have a integration. Let's try to. I think that is what we are going to do. Some here. Yeah. Okay. Uh, let's see. So so basically this f is a convex conjugate function of g, right? Convex conjugate function of g, and then we call this fg. beta. So we can view it as a function of beta. And then if you differentiate it, then okay. Uh, this is what is the okay? I shouldn't know. We we should for this one we should use this. Mm, because this guy is indeed a G nebula GP, right? Let's have a break and
예.
do it again. I forgot. Uh, okay. So one thing that I like to point out is you we didn't have a projection yet, but this one is we need this step. Uh, so basically, so this may look confusing, but this is actually a density, the left side. Because see, the point, right? Each point is a distribution density. Each point is density, and so basically the coordinate system. Okay, so point is you have a p0 and you have another one p, right? Or q. Okay, so we want to characterize certain line geodesic between the 2 point using the this dual expression, right? So using this one. So basically you this is so if you look at, you can see that this is actually you can, so this one is equivalent to eta beta is nebula G of Q beta, right? So that means this guy, you can write it as a uh, G nebula of Q beta. You see what I'm saying? See my point? So basically, now, remember, nebula G is as a was a log transformation, right? So then the left side, so this one is actually characterizing E flat distribution. Okay, and so uh, okay, so that means uh, this is after G transformation, and then this back transformation, because we now define a dual coordinate system, and then we want to characterize it back to transformation back, right? So this is a nebula F, or which is actually or uh, inverse of nebula G, inverse of nebula G. So so later we'll see that okay, so this one will actually give the particular form of the distribution function. So your q beta will be nebula f of g nebula p reference plus beta 0 1 plus beta 1 y. Okay, So what does that mean? So remember, nebula f corresponds to log. I mean, no, exponential function, right? So this is because it's just the inverse of g, inverse of log, so which is exponential. Okay. Okay. So basically, this is the this will gives a parametric form of the density function using the bases in the dual space. Okay. And now this guy itself is just this guy itself uses the uh, chain rule, right? So you need to uh, do something like this nebula. So if you differentiate with f, then you differentiate first one, and then this is basically this guy is q beta, right? Because of this. This guy is q beta. So then this guy is one. So, and then if this is beta one, then this guy changes to y, so that you have this guy. Okay. So you can see that this density form, right? This particular density form has a one-to-one mapping with 1 and m, which is exactly the same. One is this beta is more like a canonical parameter, while m is more like a mean parameter, right? So that in the exponential family, same thing. Okay. So now okay. So this is just a dual affine plane, and then we now introduce the projection. Okay. So this is for given P0. We want to minimize uh, Bregman divergence in this space. And then this guy is GQ minus GP0 minus nebula of, I mean, the inner product of nebula of GP0 and then Q minus P0, right? So then basically in terms of the because P0 is constant, so this is fixed, constant, and also this is fixed, right? So the only thing changes variable is this guy and this guy, which is this guy. So you basically minimizing this Bregman divergence is equivalent to minimize this guy. And then you apply so you take the first order differentiation with respect to Q, then you obtain this one. So then so that is basically Kuntaka condition. So that will give the Lagrangian, so then using the Lagrangian solution, you will have this one, which is exactly what we showed here, right? What we considered here. So basically, the solution to a projection has this dually flat expression. Okay, so that is the basic bottom message. So the optimization dual coordinate lies in the dual plane we already defined. But the only difference is that we have a P0 is given, right? P0 is given. So there could be many different parallel, I mean, dually flat space, but we should fix the reference point to P0. That's it. That's the one. Okay. So then this is basically our model. So that is our model solution to the Bregman divergence solution as a parametric model. And this parameter is a beta zero is basically normalizing parameter, right? So will beta will zero will make the integration equal to one, and beta one will make the mean constraint, satisfy the mean constraint. Okay. So that is about uh, the form of the Bregman projection. Okay. Now we want to discuss Pythagorean theorem. So here's a first order optimality. Okay. So Q is again closed and convex, but not necessarily not flat, not affine. Okay, not necessarily affine. Just convex and closed. Then the this solution. Okay, if solution exists, then it should satisfy this inequality. Why this matters? Basically, if you use the same argument, the the Bregman divergence can be written as this one. So you can express it as a function of phi q, okay, phi q, and then basically this constraint, this condition uh, is will be called the first order condition, first order optimality condition. Okay, this is actually intuitively, intuitively makes sense because if you let me see, I will use some. Okay, suppose you have a right, you have a convex function phi q, and so this is more like p star, right? Minimizing whatever q star. So then you suppose your r is here. Okay, then this is basically the slope will be negative. Okay, and this will be r minus p will be also negative. R minus q is also negative. So basically then negative times negative will be positive. Okay. Same way if r is here. So for any direction, right? This if you think of any uh any direction, this is more like a 3D problem, but you can imagine that you can because it's a strictly convex in any space. So then if this is right, is as long as Q star is optimal, that means you should be this product, inner product will be positive, not negative. So that is the first order condition. Because this is here, R minus Q will be positive, and this slope will be positive. Okay. So that means this one is indeed okay. So this is what I mean by that. You can think of any direction, right? R minus Q star. Uh, so like if you think about yeah, right. It's basically convex, right? I mean, but any as long as it's convex, you can cut any line, right? If you you make any this right, so then it should be positive. Okay, so there's some a feasible direction. So any direction, basically, if you construct the think of this because it is convex. This limit should be non-negative. So then that means this one is non-negative, and then this D is essentially can be written as something like I minus Q. So then you have yeah. So there's some if you I mean the proof you can is not difficult, but the concept is essentially a property of convex, and then
Here, Q star is argmax or
huh?
argmin. So in the lemma,
Okay.
so it is stated as argument of max. But it should be minimum.
Yeah, absolutely right.
It's just
Minimum. Yeah, right. Thank you. Yeah, right. Yeah, that's right. Convex, right? So it should be argmin, right? Not argmax, right? Okay. So yeah, and then tangent cone. Well, is so you can so given your Q star is like a fixed point, and then you want to create a sequence uh, converging to Q Q star with direction D. Okay, something like that. So if you think of this kind of sequence Rn, and then we will make Tn goes to 0, right? So you allow T goes to 0, and then basically this will become a limit will be D, right? By definition, right? And so for example, so tangent cone basically okay. So yeah, if your Q star uh, then is fixed, then your Q. So AQ is B. I'm talking about this one, and then AQ star is also B, right? Then means AQ minus Q star will be 0, right? And so that means this guy will be in the corner of A. Right? Well, this is just a mathematical irregularity, but point is the important result is this one. Okay, first order optimality, and then we can use that to show Pythagorean inequality easily. So Pythagorean inequality is about convex Q, so not affine. Okay, so the whole story is okay. If the subspace is convex, then we only have one part of the equality, one part. So as long as this Bregman projection exists, it will satisfy this particular inequality. Okay, and then if we in addition we have affine, so not just the convex and closed, but also affine, then we will have equality. Okay, so and why? Because and this proof itself is pretty much obvious, because this is if it is convex and Q is Q star, right? For Q star, we know that this is indeed non-negative by the first order optimal first order condition. this one. First order optimality condition. FOC. Okay, so that we have this one. And then basically if we have equality in this inner product, then we'll have a equality in the Pythagorean theorem, right? And so how to show? Okay, so then here's the Pythagorean identity for affine. Okay, so we know the Pythagorean inequality says that this is have this one, and then with equality if this inner product is 0. Okay, and now the if you have I projection, the Bregman projection, we know that this will satisfy in the span, right? That is the Kuntoko theorem that we already have seen here, right? So that basically will show. Okay, so basically we have this one, P0, okay, P star actually, because this P star is our solution, right? So the projection will be G P0 plus lambda 1, lambda 0 plus lambda 1 y, right? So this is the result of Lagrange multiplier method. Okay. And now point is this guy, right? This guy is because of this one. This guy is equal to lambda 1, lambda 0 plus lambda 1 y, right? And then because of the this P and Q star are all belong to this affine subset Q, right? So that means we have 0 because of this. So that means the equality holds, and as long as P is in this affine, right, and flat subspace. So that shows the establish the Pythagorean theorem. Okay. Now, so this is, remember, this is modeling, right? So the Pythagorean theorem is just a projection, and the projection has a particular form which satisfies the this orthogonality of the inner product pairing, and so then we have a nice result. And now let's talk about estimation. So not about modeling, right? Estimation. So the estimation means that we want to do some sort of a M projection with the sample data. Okay. So the E flat, one particular projection gives the model, right? So the model is indeed can be written. So this is our model. So you have a parameterization. Theta is your parameter, right? A is just a normalizing constant. Now I use the Ty intentionally to emphasize that it's just a surface statistic, right? Surface statistic, which was originally came from the Q, subspace Q. Okay, and so then now how to do estimation? Remember, in the estimation, we use in the E flat model, right? E flat model, the estimation is minimizing KL with P hat and P theta, right? because that is actually MLE. So that is actually M projection, right? So we are going to do the same thing here. So basically we have a KL now changes D, right? G, and then we have a P hat and given the model. So we project, we give a Bregman projection on the model space from the sample space, right? From the sample, from the data space to the model space. That's it. So that is estimation using Bregman projection. Okay, and now turns out that we can use the dual form, right? If you use the if you remember the dual form, then turns out that this one can be written as something like this, which is essentially uh, is kind of will show some you can treat it as a log likelihood. So it is not log likelihood because we didn't really take a log right here, right? This is Bregman. So this is essentially log likelihood version of the divergence in the using Bregman. Okay, which is this one. So we need you need to use the dual function. Okay, so then basically if you apply, so if you differentiate with respect to theta, so if you differentiate, remember, if you differentiate theta with respect to log likelihood, you get scope function, right? Okay, what about, but this one is general. For our general setup, turns out that a differentiation of this L gives a moment matching equation. Okay, which will give you a estimation formula, right? So that is a very nice, estimating formula for having this information projection, interpretation. Okay. So the right side is a sample, right? So the right side is a sample moment of the surface statistic, while the left side is a model moment, right? Model moment of the surface statistic. And we equate and solve for theta. Okay. So then we have some,
You're basically saying that when using that construction, then we'll get back to the matching moment matching kind of work.
right.
So you can use different kind of model.
So
And you minimize the ground distance due to different aspects.
so yeah, well, yeah. So okay, if you know is for the parametric model, we just use log likelihood and compute the maximum likelihood estimation. But that has a essentially minimizing Kullback-Leibler divergence, right? As an interpretation. But for the general Bregman divergence, why should we use Kullback-Leibler minimizer, right? I mean, for parameter estimation. And maybe this one, I don't know whether I don't this yes, I think there's some this area called minimum divergence estimator.
You could use different divergence.
Right.
And then that will give you kind of different families of different.
Exactly. Right. So you choose different G. Say, for example, you can use Hellinger divergence.
One
And
choice will correspond to the likelihood.
right. That's
the
right. Right.
So also about the dual alpha family, that form,
Mhm.
that also can be changed, right? Why you have to use that form?
You mean
The
dual fine.
Yeah.
So this one, remember this one comes from the projection all the way.
Yeah, because that space is defined by you, right?
So that space
This
by
space is like you're talking about, all this is based on projecting to that space. With normalizing to one and with the.
So we have a-
Yeah,
Initially, our Q is a moment, right? Suppose we have a moment assumption,
yeah.
and then we want to project using Bregman divergence.
Can you just project it in a different space, not just have the moment?
I see.
Yeah.
So I think as long as you can construct a flat space, flat space, I mean, affine. Okay, so because this Pythagorean equality only can be established by affine space.
Yeah, so this is the Q, right?
Right.
Right. Space. But is the general theory only about the affine space, or is it also applied to other space?
Affine space. Yeah. So I mean, this equality is only for the affine space. Yeah. Yeah. So yeah. But now actually, so you could actually consider some is, you may allow this M could be unknown and do some other things, but yeah, fine. So this Pythagorean is only established for the affine dually flat. We use dually flat, but there could be other approach too, but I don't know. Okay, so that is the main thing. And now let's extend it further with the covariate regression problem. Okay. So you have suppose you have a covariate, and then basically you have this function, okay, mx, and suppose you know this one, and then you want to use it to build a space, right? To build a fine space, and then apply the projection. So that is the goal. So we now the space is a conditional, the space of the conditional distributions, because we conditional on x, okay. And then minimization, right? I mean the Bregman divergence projection. We use the same Bregman projection, but the space is now satisfies this particular form, integral equation, which basically says because you okay, if you know m is a marginal mean, right? If you know this assumption, then you can construct a single equation, single integral equation, right? Like y minus m, p py d mu y, something like that. But now this is because this is conditional. Your equation, your integral equation has actually double integral.
What's the T? T1.
Huh?
Regarding restriction on T, the T is a function of Y, right?
T is known function of y, right? You can make it just y, ty equal to y.
Yeah, but it can also be any function of Y.
As long as you have a model assumption. I mean, so because this is a given, right? So suppose you have an assumption that that mx is a known function, and for the known function mx, you want to construct the projection.
So if we do a simple linear regression, Ty becomes beta 0 plus beta 1x, something like that?
No, actually, ty is just y.
Oh, I understand.
Okay.
So
mx is right. mx is linear.
You
Okay.
can look at the multiple functions of Y
Uh-huh.
and say, oh, we don't have the Y, value of Y, continual X is a linear function of X. Explanation of Y squared, continual X is another function of X.
Right. Yes. Okay. So
So those can be done, like, you can calculate first moment, second moment. You can put so you can have a higher moment,
mhm,
can lead to
Okay.
there, but.
okay. So then we want to basically do the same thing. Develop the eye projection. So this is essentially Bregman divergence, right? Q and P0. So P0 is essentially initial point. So here the point is essentially all conditional density, right? And then constraint is this one, and M is we already defined M before. So then we can apply a Lagrangian multiplier method, and then apply Kuhn-Tucker state condition to get the functional form. So end of the day, this is our form.
But this is assuming linear, right? You don't have to be linear.
So yeah, so that is actually a good point. So basically, I do not fully understand why. I think eventually they want to create a linear model. So that's probably why. So you are implicitly making a simple assumption. Okay. So yeah.
Well, obviously, a linear model will be easier to solve, but I don't see why the MX, well,
Right.
they didn't put a constraint on MX, right?
So yeah. No, right. MX is we don't have any constraint on MX per se at this point.
We could
But-
use like this one or something. For MX.
But later we have some hint, but I think so. Yeah, right. Because because here the space M space the convex the affine space that we define is actually a special space where this is the it's orthogonality. So you have a residual. It's orthogonal to x, right? I mean y minus y hat is x. Is right. So it doesn't really make a arbitrary x function of x. So I think this is to make the problem parametric model. To make a parametric model, you create a finite dimensional basis function.
You could change like X into some basis function of X.
Right.
That-
That's right.
that would-
Right. Yeah. So that's right. So then eventually we have a parametric model, right? Parametric model. And so we can basically do the same optimization and projection and so forth. So this is basically characterizing how your parameter is related to your moment condition. And then, so this is basically modeling part. And then parameter estimation part, as we did before, we will use this one. So Bregman divergence projection, right? Between the data point and model. So this is the data and model, right? And then the solution will be like this. So which is essentially equating the so this is a more like a score equation, right? So this is actually turns out to be GLM score equation.
Just like as many, like, there is a method of moment type of thing.
Yeah, right. Yeah.
But then, how does that, T, change any of this?
G?
Where is, how does that, estimate equation depend on G, the Riemann, divergence, right? If we use different divergence, but if the same.
That difference by expectation.
Q, right. Q depends on G actually. Remember. So because Q depends on F. F is actually dual of G, right? And so it's right, right. So that is basically what is going on. Okay, here. And then yeah. This is that
So this can be considered as a generalization of the generalized last limit equation.
right, right, and or generalized linear model, right? Yeah. Oh, I think I covered that already. And so, yeah, I think this is a kind of wrapping up. So I see. So here I like to make some connection how this is really related to GLM. And so, so because this particular one itself is just a modeling, right? I mean, this one is the same model, which is a solution to the Bregman projection. Okay. Now, now let's use G. So in the GLM literature, they use basically this solution, right? I mean, this is a GLM form. So in the generalized linear model, they have a canonical parameter. I mean, this eta I and eta I is a G of mu I. So this is what? This is right link function, right? GLM link function. So there's some I think so what we ended what we have can be formulated as a GLM, and then one interesting part I found is that your deviation, right? The deviation here uh, can be turns out to be the convex conjugate Bregman divergence. So remember, this is what. So this is data, and this is okay. So this is Bregman divergence between data and the mean. It's mean, but this now you need to use the dual convex conjugate function. So that I think is kind of so you because you later this. So this deviation is a kind of measure of a fit, right, in GLM, and that turns out to be has a Bregman divergence interpretation.
But KL is a special case of Bregman divergence, right?
I'm sorry.
The KL divergence is a
Yeah,
special
right,
case.
right.
And the usual deviance is an interpretation as a KL divergence.
Right.
So it is not surprising that it can
Okay,
be
okay. Yeah. But there's something that I couldn't fully figure it out. But yeah, because in the very beginning we have all the general Bregman projection, but at some point we just consider the special case and make a exponential family, and so from here we just use the particular G function, which is the entropy, right? Negative entropy, and so that we the solution can become a exponential family.
It's connected to the KL divergence, right?
Yeah, right, sure.
So
Yeah,
if you use a different Bregman divergence, you will have a different family. There, right?
right.
You are not
But not necessarily
have
exponential family, right. So because the GLM, so my question is probably this. So GLM literature all uses the exponential family,
Yeah, exactly.
right?
So now you can generalize.
Right.
All the kind
That's
of-
right. That's right. So maybe there's a way to generalize it further. So but that is basically what I kind of understand. But yeah. So that's the main thing. Basically, this guy, which is the unit deviance, which is the using based on the log likelihood, turns out to be using a dual of the Bregman divergence. But yeah, I think that's pretty much all. So so this flat, we started with the mixture flat, which is M flat, right? M flat. Then we were able to get some particular form, which will give us some parametric family. And then
Mixture flat is E flat.
no, Q is M flat.
Mixture flat denotes E flat. In exponential family, the theta, the upper in the exponential is log flat.
No, the Q, we are talking about this particular Q. I mean, the Q that we started with, which is the mixture.
I think this Q and F is flipped with the definition of we defined. Here, F is what we defined with Q in previous page.
Okay, well, so I'm talking about this one. I mean,
That Q is M flat, yeah.
yeah, that is M flat.
But here, F is that Q.
Okay, let me see. Okay, right. I see. You mean the dual so you mean the G? Is that your point?
Make
Or
that should be Q.
I see. So I see your point. Okay.
Mixture flat is in example, mixture flat is exponential family, and this restriction is same mean M flat.
I think no, I think Q. So here, what I meant was like this, P equal to 1 and P y equal to M, right? So this is M flat,
Yeah.
M flat, and then from there we can actually construct some kind of a G P G P0 plus lambda 1, lambda 0 plus lambda 1 y. Okay, so that will give this form. Right?
Yeah.
Okay. So anyway, so that is projection, right? I mean, and then we can even extend it to the regression type problem too, using this Bregman divergence measure. But yeah, there's should be a lot of things to explore, but this is probably these 4 lectures are pretty much the basic preliminary stuff to understand, to move on to any of your research. So I think I will stop recording.